Hello. So hi. Maybe you can try to share your screen.
You should be able to see.
Yeah. We see the slides. Perfect.
So we can go to full screen also. Is it okay?
Perfect. Yeah. So thank you, Angelo. So we welcome Angelo Bassi, who is going to talk about present and future precision tests of spontaneous wave function collapse models. So like every time, so around 45 minutes, 50 minutes of talk, around 25 minutes of discussion, and whenever you want, Angelo.
Okay. So thank you very much for the presentation, for the invitation also to the workshop. So there is a kind of a shift now more to theoretical physics with respect to the previous talk, and also some experimental physics. I'm a theoretician, so I will not say really much about that, just perhaps the results. So as the title says, I will talk about models of spontaneous wave function collapse with a specific attention on possible ways of testing these models, which is what I've been working on in the last years or so, almost 10 years by now, we will say. And these slides, the introductory slides are something you very well know, and so I will not spend much time except for saying that so the problem with understanding quantum mechanics, that you know, it's not just now a problem of philosophy, it's also a problem of physicists. And more physicists actually acknowledge that there is indeed an issue with the theory. And so Einstein, everybody knows about that, also Weinberg, Leggett, and also Penrose recently won Nobel Prize and is one of the almost, many theoretical physicists with Nobel Prize winners that appreciate the problem with quantum theory. So the consensus is growing that there is something to do with that needs to be done with the theory. Perhaps there is no consensus about what should be done, but that's also somehow understandable. The problem is, of course, is the linearity of the theory when you assume that the theory has a universal validity, so it should apply to every physical system. And perhaps, one way to look at collapse models is to acknowledge that this is not true in some sense. That quantum theory is the theory of microscopic systems, and when you come to macroscopic objects, there should be a different theory, or perhaps they both are two sides of a new theory of nature yet to be discovered. Okay, the Schrödinger-Katz paradox. I will not spend much time with that. And then you know that in standard quantum mechanics, somehow whatever standard means, let's say what you read typically in textbooks, or what you used to read in all their textbooks, is that there is a divide between a quantum world, which is governed by the wave function, and there is a classical world. So there are classical observers that decide what to measure. They have classical instruments, and the wave function is a mathematical tool to infer probabilities about the outcomes of measurements. And then there is a problem. There is an interpretational problem, but there is also a problem for theoretical physics. It's not only a problem of interpretation, it's a problem of the theory. As Weinberg, many people, said this. I like this clear quote of Weinberg that the standard quantum mechanics assumes this mysterious division between the microscopic world governed by quantum mechanics and the macroscopic world of apparatus and observers that obeys classical physics. And this is fine from the phenomenological point of view. And actually, this is my take about quantum theory, as we know it, is a phenomenological theory. It works very well, no question about that. But like many phenomenological theories, they have a limited range of validity, and also from the conceptual point of view, they are ill-defined. And so, in that sense, there is no surprise that there is this arbitrary quantum to classical divide. But if you want to take the theory seriously as the theory of nature, we have nothing better at the moment. So many consider this, they would take this as a fundamental theory of nature. Then there should not be this arbitrary divide between quantum and classical, between micro and macro. There should be a unique, or at least you would expect from fundamental theory to have a unique description that possibly as clear as possible. So the goal of quantum foundations, at least from the point of view of theoretical physics, is to remove this divide or to make it more precise in some way or another. So typically, theories and interpretations like Bohmian mechanics or many worlds remove the divide, so you have a universal description of nature. In collapse models, instead, you somehow give a more clear definition, a dynamical definition of what is micro and what is macroscopic. So in these models, I guess also this is something that, so I'm going a bit fast at the beginning because I think that most of you know this kind of things, and so I don't want to spend too much time, but in case you can, anytime you can stop me and ask me questions if you wish. So the idea of collapse models to resolve the measurement problem, this micro to macro transition, is to modify the Schrödinger equation. So the Schrödinger equation is not linear anymore, and then you do not have the Schrödinger-Katz paradox, which comes from the linearity of the theory. So that's the fundamental idea. So the fundamental equation is non-linear, and non-linearities, of course, have to be injected in a suitable way, because not every way of doing that is consistent. You do it in such a way that at the microscopic level, you do not touch the Schrödinger evolution that much, so that the quantum properties of microscopic systems are preserved, except for tiny deviations. And actually, these tiny deviations are what you look after if you want to test these models. But when you come to the macroscopic world, then there is an amplification mechanism, which I will tell about, that ensures that the nonlinear effect becomes dominant when a large number of particles interact with each other in such a way that the cat, just to take an example, being from the physical point of view, a system with a large number of degrees of freedom, a large number of particles, the wave function is always the wave function describing the cat is always well localized in space. So well localized in space that it behaves for all practical purposes like a point, moving according to classical dynamics. So in this sense, in collapse models, the point-particle description of the classical physics is an emergent phenomenon. At the fundamental level, you have the wave function. Then the question is, what do you do with the wave function? Since the wave function doesn't live in real space, it still lives in configuration space. I will kind of postpone this to the very end of my talk, but let's forget about that so for the time being. And so I was saying that in collapse models, you have a fundamental wave description of nature, but these waves have a solitonic solution. The solitonic solution becomes more and more prominent, sharper and sharper when you move from the microscopic world to the macroscopic world. And the soliton becomes sharper and sharper, smaller and smaller, so to say, and you can basically treat it as a point moving in space. This is the way in which you give sense to quantum theory according to these models. Okay, so the GRW model is the first consistent model that was presented in 1986. There were, of course, many attempts before. We have Nicholas here that worked on these ideas during those years and before that, and Philip Pearl in the US. So it was a line of research which was followed by different people, Lajos Diósi, just to slowly recalling everybody. So in the GRW model, basically you have a piecewise dynamics. The wave function evolves according to the Schrödinger equation, except that at random times, in random points of space, it collapses. Mathematically, you have the collapse is just what you would do mathematically. You take the wave function, you multiply it by an operator, and then you renormalize the wave function so that to localize it in space. And this collapse operator is a Gaussian. Nothing special about a Gaussian function. It's just a decent localization function. The collapse is random in time. You would take a Poissonian distributions for the collapse times because that's the easiest thing to do. And then it is governed by just one parameter, the rate lambda, the rate of collapse of a single particle. So this is one of the phenomenological parameters of the model. And then the collapse in space, you would take somehow proportion given by the Born rule in a way or another, because you want to recover the usual quantum probabilities when you describe a measurement process, and L times psi, what you see in the slide, square modulus of, just does the job. And then the Gaussian has to have a finite spread controlled by the parameter RC, because if the spread is zero, so if you have a direct delta, then the model in principle could work, but is physically inconsistent because it destroys matter. Basically, you are localizing the wave function too much. You are making matter unstable, and you would have particles jumping here and there, and so the model wouldn't work. And so you need also a finite localization with RC. So lambda and RC are the two phenomenological parameters that characterize the GRW model and the CSL model, and more or less any model. You can have one parameter instead of two, but you need somehow a parameter, and you can try to give a physical meaning to that. Okay, just a few pictures to see, just to have a better intuition of what goes on. If you have a wave function which is wide in space, very well spread out, and then a collapse occurs somewhere at around position x, then by a simple multiplication, you see that the wave function is immediately localized in space with the resolution given by RC. Of course, there are these tails going off to infinity, but most of the wave function is in a well-defined region of space. The jump probability, the collapse probability, given by the formula that I showed you before, morally, not exactly, but morally amounts to the area within the Gaussian jump function and the wave function itself. So the area in the circle there. And then you can easily see that the probability to have a collapse around x is larger where the wave function is more appreciably different from zero. So actually in this picture, this would not be the first choice for the collapse. Do you see my pointer? Can you see my pointer moving? So if you see it, so basically the collapse is more probable to occur here or to occur there. I just picked this point here just for the sake of the picture. Okay, so again, something simple. If you have a special superposition, which is something what people usually consider a superposition of two states localized here and there, then nature decides to have a jump either here or there because the probability is different from zero, basically only around this region or around that region. If it collapses on the right, then you kill the wave function on the left. The probability is 1/2, what you would expect and you would naively do. However, and this is important, not so much from the conceptual point of view, but it's important from the experimental point of view. If you have mathematically speaking, if you have a superposition, but the two terms of the superposition are close to each other with respect to RC, which is this phenomenological parameter of the GRW model, then if you try to collapse the wave function, basically you can't. Because the Gaussian that controls the collapse is too large and is not capable of selecting one of the two terms of the superposition. This is important because it tells you that not all mathematical superpositions are suppressed from the physical point of view. And indeed, experimentalists now are capable to create, and they will do even better in the future, they are capable of creating superpositions that are small, they are close to each other in space, but technically they are a superposition. And so experimentally, this is something that nature allows. And so if you have a collapse models and you want to have a consistent collapse models, you have to take collapse model, you have to take this into account, that you should preserve some superpositions and not, and while collapsing other superpositions. Okay, the amplification mechanism. So this is the important point. So the important point of, and the main reason why people are talking about collapse models. So if you take two particles, and then the game becomes quite easy if you have n particles. So the two particle description is sufficient to describe, to understand any other physical situation. So suppose that you have two particles which are entangled with each other. It's like a diatomic molecule, which can be here plus there, like in the picture. So technically, it is an entangled state. Technically, this is important, actually. So if you have two particles, then nature decides to collapse. One of the two particles. If you have two particles, of course, again, I will postpone this discussion to the end of my talk. I should not talk about particles in collapse models because particles basically means a point-like particles. Here, it's not clear whether you have point-like particles. So I use the term particle in the sense of a constituent or whichever way you want to call it. So if you have two particles, you have an independent collapse process for each of the two, each of them. So suppose that nature decides to collapse on particle 2, like in the picture, decides to collapse on the right. It could have happened on the left, it happens on the right. Then by a simple calculation, you see that the collapse of the wave function referred to particle 2 brings in also the collapse of the term of the wave function referring to particle 1. Or in other words, a collapse of one of the constituents causes the collapse of the entire system. And so this is the reason why you can describe you can have the quantum to classical transition, a quantum description of microsystem and the classical description of macroscopic classical objects. If you take the Schrödinger cat, the usual example, and you try to create a superposition, then what happens? It happens that in a time given by the number of particles, so 10 to the 24, how many particles are there in a cat? 10 to the 24, more or less, divided by the average time of a collapse for one single particle, which is supposed to be 10 to the 16 seconds. So a collapse for a single particle occurs once every 10 to the 16 seconds, almost never. But if you have 10 to the 24 particles, then in 10 to the 24 divided by 10 to the 16, which means in 10 to the minus 8 seconds, something happens. Almost in a split second, some constituent, some particle in the cat will suffer a collapse, and which will destroy the superposition that you are trying to create. You're not even capable to create a superposition. It's not that you have a superposition and the superposition collapses. This is an academic description of the situation. In collapse models, you are not even capable of trying to create a superposition of the cat, that almost immediately a collapse destroys the superposition. Probably the amount of energy required to be so fast in creating a superposition of the cat, I don't know, I never made a calculation, but it's beyond the current experimental capabilities. So the cat is always localized in space. Or if you take a measurement process and you have the usual pointer, the typical way of describing a quantum measurement in an idealized way, at least, it's not the pointer the unitary evolution would try to create a superposition of the pointer by propagating the microscopic quantum superposition to the macroscopic world. But the collapse will prevent this from happening. The pointer will move randomly in one direction or another and will give the different outcomes of the measurements, which will be distributed according to the Born rule. So the moral in this way is that with collapse models, you have a dynamical description not only of microscopic system, but also of macroscopic objects and also of measurement processes. You don't need to have extra assumptions, whatever, about measurements and observers and observables and whatever. Everything can be derived in a way or another from the dynamical equation. And of course, this amplification mechanism is not always there, because suppose that you take the two particles, but the two particles now are not entangled, they are not bounded together, but they are independent, like in an ideal gas. One goes one way, the other one goes the other way. They are both in a superposition here plus there, so they're both delocalized. And again, suppose that nature decides again to collapse one of the two, to have a collapse on one of the two. For example, again, for particle 1, particle 2, this time on the left, as the picture shows. Okay, the wave function related to particle 2 will collapse. But since now you have a factorized state, and factorized is a mathematical way of expressing independence between the two, then the collapse on particle 2 will not affect particle 1. Particle 1 will still be in a superposition. So what does it mean? That when you have a gas, suppose that you have a gas, and suppose that in some crazy way, but I mean, it will be possible perhaps. So you have 20 to 24 particles, and each of them is in a superposition. So not the gas here plus the gas there, but the gas is somehow somewhere, and each particle is in a superposition. So like with the cat, every 10 to the minus 8 seconds, a particle will suffer a collapse, but it will not bring the other particles along with the collapse. So the gas, as a macroscopic system, will remain in this funny quantum state. Just from time to time, a relatively small number of particles will suffer a collapse. And this is important, again, not so much from the conceptual point of view, but from the experimental point of view, because experimentalists now are capable of creating this kind of gas where particles are separately in a quantum superposition, like a cold atom physics and these kind of things. And so collapse models will be disproved experimentally if they were not capable of describing the quantum properties of such complex systems. Okay, so basically it's not, so typically the short version of the story is that when the number of particles increases, then the collapse, then you trigger the amplification mechanism and the collapse becomes stronger. But this is not technically correct. It depends also on the state of the system. And so the summary of all this is, I hope, I mean, this is one way to present it, is in this slide. So if you have a microscopic system in a superposition in space, here, atom here plus atom there, nothing happens. Modulo tiny deviations, and again, this is what I will talk about now. If you have the cat here, cat there, table or whatever, crystal here, crystal there, then you trigger the collapse, the system becomes immediately classical. If you have this new complex quantum system where you have separately the constituents in a quantum state, not so much happens. Again, you do not have the amplification mechanism, something happens, but nothing dramatic. And then what happens to the other degrees of freedom? We like spin, as I somehow I show in the picture, or momentum or energy, whatever. Well, nothing happened to the other degrees of freedom unless a superposition in this degrees of freedom is turned into a superposition in space. So in collapse models, as you well understand, there is a preferred basis, which is space, and only when you have superpositions in space, then the collapse comes in and tries to kill the superposition. If you have a superposition in other degrees of freedom, they remain there unless they do imply after some time, for example, a superposition in space. This is a typical example with momentum. If you have a superposition of two particles with different velocities, then the two terms of the superposition will travel in different will be after some, they will travel with different velocities. And after some time, will be in a superposition of different positions in space, and then the collapse kills one of the terms. So also, a momentum superposition is also localized, but not because it's a momentum superposition, but because it triggers a position superposition. Okay, so this was the GRW model, which well describes basically every collapse model. Now I just want to show you some equations, since I mean I'm a theoretical physicist, so this is the way I work with, and just to give you an idea what it is about. So this is the equation of the CSL model. CSL, continuous spontaneous localization, is basically the continuous version of the GRW model. And there you see clearly that you have the two types of dynamics, the Hamiltonian, which gives the quantum properties of matter, and then the collapse, which keeps classical systems classical. What's there to say? So there is this preferred basis, the position, which is mathematically expressed by the mass density operator M, which is equal to small m a daga x ax, creation annihilation operator. Nothing important, is the mass density. It is an operator that describes the mass density, and the key word is density here. Density means space. This is what gives the preferred basis in collapse models. You see that the equation is nonlinear because psi and psi enters the equation. So the equation enters basically 3 times into the wave function enters 3 times into the equation with a third power, let's say. And so it's nonlinear because you want to collapse the wave function. It's also random, and you have a noise W of t. It is a linear process in time. So delta correlated in time, just because things are simpler, no other fundamental reason. And it's not delta correlated in space for the reason I told you before, because if it's delta correlated in space, then this noise is too violent and it destroys matter. So you need to have some smeared correlation function. And then you take either a Gaussian, and again, this is the original CSL model, the evolution of the GRW model, or you can take the Dioschi-Penrose model, the DP model, and you have a Coulomb type of correlation function. And these are basically the two choices which have been considered in the literature. You can make your own choice. There is no fundamental reason behind that. There are just some arguments. I just want to note that in this form, the CSL model, like the GRW model, is defined in terms of 2 parameters. There is again lambda, the rate of collapse, and RC, the width of the Gaussian. In the GRW model, it was the collapse Gaussian. Here it's the correlation function of the noise, but morally it's the same thing. In the DP model, and instead, in this slide, then things will change, there is no free parameter, because you have that somehow the idea is that instead of the rate, lambda, you have a capital G, gravity, over h bar. Of course, the dimensions are not correct, but you can fix this. But morally, let's say, instead of a phenomenological parameter, lambda, fixing the rate, you have capital G, the gravitational constant, giving you the strength of the rate of collapse. And then instead of the Gaussian, where you have to define a width, you have the Coulomb potential, which has somehow a natural width, so to say. Of course, this natural width is infinite, and then I will come to the problem. But let's say that it has a natural width, and so you have no parameters. And this is actually one way in which one reason why Dioschi was happy about this model, because it was free of parameters. And so you just test it. It is either correct or wrong. And of course, it also has a gravity flavor, because there is a capital G. And actually, I will come to that. So to Penrose and collapse. So here, I just want to say that basically this is the end of one part of my presentation up to here, just how collapse models are supposed to work. I hope, if there are questions, you can ask me, otherwise I'll move on. So there is the collapse of the wave function there is. So why should there be a collapse of the wave function? Well, one simple answer is that it could be because nature is like that. That's how nature works. There is an intrinsic stochasticity. There is in nature, it happens to be like that. And then we have to describe it in terms of a stochastic differential equation. And I think that, as far as I understand, Nicholas would subscribe this point of view. Other people, and he can add more if he wishes. Then other people, for example, Dioschi, as I mentioned, or Penrose, and I want just to spend some time here, they would try to find a reason why the collapse occurs. The collapse occurs not because nature is simply like that, but the collapse occurs because there is a physical mechanism which happens to trigger the collapse. And that physical mechanism is gravity. And so I try to somehow to summarize what Penrose says in his papers about that. So he has an intuition about how a quantum theory of gravity should look like. And in particular, he says that the following should happen. That when you have...
I'm sorry, Angelo, sorry to interrupt. Just Aurélien need a clarification on the previous slide. So
please.
Okay, yeah, sorry, I didn't. I just write it. Okay.
Just just to stop me anytime, because I'm not seeing the chat. So if you are,
I'm too slow, it's reason.
Okay, for everyone, the best is if you have clarification question, you can ask them. But if not, maybe keep your question for the discussion after the talk, of course.
So then I will be short. I wanted to know how you can distinguish this kind of model from decoherence, because the formalism is very similar. And yes. What happened also if the lambda that you put in your, the RC which appear in your model is going to 0?
No, so can you, the second part, can you repeat the second part of the question?
Yeah, the second part of the question is what happens if you Gaussian in your different model, the continuous spontaneous localization model or the GRW model is going to 0, it's the size of the Gaussian.
Okay, so I first answer the second part because it's shorter, then I will answer the first part. So if the Gaussian goes to 0, then what happens? That you localize wave functions too well in space. And in particular, what you can prove is that if you take the hydrogen atom, you immediately ionize the electron. So the wave function of the electron becomes too narrow, and so it's not a bound state anymore. And basically what you would see, so mathematically everything works in a way, but the point is physically. Physically, what it would happen is that electrons should come out of matter, or that molecules are broken. Because again, you have a bound state of the molecule, you localize one of the two too well, and then you break the bound.
There's a constraint, it's an experimental constraint.
It's an experimental constraint. Yes, it is an experimental constraint.
Okay.
So of course, I mean, you can be mathematically picky and say that R equal to 0 is not acceptable because Dirac delta functions are not functions in the Hilbert space. You can be mathematical picky, but as a theoretical physicist, I don't care. Dirac deltas are okay. So the constraint is not mathematical, the constraint is physical. The model would be there, but it would be physically inconsistent. So did I answer? Okay. So the first part of the question, so the story is a bit longer, but I am happy to answer that. So the master equation of collapse models has the same structure as that of decoherence. It's a Lindblad type of equation. You can make it non-Markovian, but also decoherence can be made non-Markovian. So let's say it's a master equation. So from the conceptual point of view, there is you cannot distinguish the two. But the story is less simple than that. So first of all, suppose that you make an experiment and you see a lack of quantum properties because either of a collapse effect or of decoherence effect.
Okay.
Then in principle, you know the sources of decoherence. It is collisional decoherence with the gas molecules. It's a thermal emission. So you have you never have a vacuum in your experiment. There is always some residual molecules which cause a little bit of decoherence. Or you are never at zero temperature. So your particle will emit some photons and this will also cause some decoherence. So all these decoherence effects, at least I'm talking in principle, are all well known from the theoretical point of view, and they have a precise behavior, and they have a precise dependence on the parameters of the experiment: pressure, temperature, mass, density, and this kind of things, which is different from that of the CSL model. So again, you can in principle subtract known decoherence effects, and then you are left with either something or nothing. So if you are left with nothing, then okay, that's the end of the story. There is no collapse modus. Then there is no collapse effect. But suppose that you are left with something. Then what happens? It means that something is not explainable, is not explained, but what you know. So then already you have achieved something. You need to assume new degrees of freedom. Something new in physics you need. It could be a new particle, and still you are in quantum physics, linearity, measurement problem, and all these kind of things, but at least you have achieved something, you discover something new.
Okay, great.
So, and that's the best you can do at present. I personally think, but that means but if I say think, it means that I'll never prove at the moment. I personally think that it is possible to go slightly beyond our present knowledge and find an empirical way to distinguish a pure collapse effect from a pure decoherence effect, which means going beyond the usual way of using quantum mechanics. Yeah. I wouldn't say more about that because when I have the model, when I have the ideas written on papers, I'd like to talk about that. So I just say that I have the intuition, the feeling that you can find an empirical way to distinguish between pure decoherence in the standard quantum sense and the true nonlinear collapse effect. But with the present status of collapse models, this is not possible.
Okay, great. Perfectly clear.
Sure. And okay, so I move on. So okay, Penrose. So quantum gravity, as I said, so Penrose has his intuition about what a quantum gravity should be. And in particular, he says that when you have a superposition in space, and again, since it's gravity, so it's about space, so there is in a quantum language a preferred basis. So when you have a superposition in space of mass, you create a superposition of space-time. So if you inject a little bit of quantum gravity ideas, so you work in a weak field limit where things are somehow clear. And of course, the larger the system, the stronger this curvature of space-time, the more somehow there is a superposition of different space-times. And then he believes that in a true quantum theory of gravity, in the correct quantum theory of gravity, the dynamics does not tolerate the superposition of different space-times. Actually, because the dynamics is not well defined, because the dynamics is it should be defined in terms of an evolution operator, and the evolution operator cannot be uniquely defined in a quantum space-time. And for Penrose, as far as I understand him, of course, this lack of capability of uniquely defining a time evolution for a quantum superposition of different spacetimes implies an instability of the dynamics itself. So the evolution is not well defined, is unstable, and wants to go back to a well-defined situation, which is basically a classical space-time. So the moral of all this is that superposition of mass, of matter, implies a superposition of space-time, which is unstable, wants to collapse, and the collapse of the space-time triggers also the collapse of the wave function. Okay, so he acknowledges that he doesn't have a mathematical model or a theory for that. It's just his belief, his strong ideas about how the correct quantum theory of gravity should look like. But he tries to give some phenomenological content to that. And so he uses, and you see it basically in the slide. So this slide is due to him. So the credits go to him, of course, for the slides. So he says, the best he could do, and actually, I mean, it would be very much hard to go beyond that. He says that you can give an estimate of the collapse time using the usual Heisenberg relation between energy and time. So T equal to, so the time of collapse, so the instability, so the measure of the instability of the And of the decay of the superposition is h bar over delta E, where delta E is the gravitational content in a way or another. You can measure it in slightly different ways, but the moral is the same, is the gravitational content of the superposition mass here plus mass there. And in a classical, in a standard laboratory situation, the gravitational content can be computed using the Newtonian potential. You wouldn't go to extreme gravitational or high velocity situations. You can do some tabletop physics here. Okay, so this is the idea of Penrose, and what Diyoshi did basically, actually before Penrose, is to give a dynamical evolution, a dynamical model which implements these ideas. Penrose would say that it's not the way he would do that. I'm just saying that Diyoshi did present a way of doing that, of describing dynamically this collapse with the time, which morally is equivalent to Penrose's guess that you see in the picture. And this is actually what I showed you before. Basically, this is the equation. It's always a collapse equation, and then with the G defined as in this slide already. Okay, so this model, so the first thing about this model, since they explicitly violate the Schrödinger equation, and you would test them on perhaps people would do other things, but one interesting thing is to test them experimentally to see whether you can test them. And this is actually my job, has been my job in the last years. So how do you test these models? There are two ways: interferometric and non-interferometric experiments. Interferometric experiments is the double slit experiment, basically, and that is the first thing you would do, since the whole business here is about the superposition principle, the Schrödinger cat, whether you have macroscopic quantum superpositions or not. Then what experimentalists should do is to take a system which is as large, as massive as possible, create a superposition in space which is as large as possible for a time which is as long as possible, and then see whether you see quantum interference or not. And there is a simple picture there, and I think that Marcus Aspelmayer spoke about that, how the difficulties and the challenges and the great adventure in trying to do them. It's a long journey, but the experimentalists will arrive there one day or the next. So you do this superposition. Ideally, you do in a clean environment with little or no decoherence. So quantum mechanics tells you that you should see interference. Collapse model tells you that you shouldn't see interference if the superposition is large enough. And then you have a way to discriminate the two. Nice, but difficult. Another way is the following: are non-interferometric experiments. Non-interferometric experiments are based on a diffusion process. So the idea is given the picture there. Every time you collapse, you move the wave function. You change the wave function. Changing the wave function means physically also slightly changing the center of mass of the wave function. Because usually when one presents the collapse mechanism, one puts the Gaussian precisely on top of the wave function, but this is not what happens mathematically. The wave function, the collapse can be slightly here, slightly there, it can move around. And when you move the collapse around, you move the particle around. Or much more simply, the collapse is random, it's described mathematically by a noise, and then the noise does the job that every noise does, moves the particle in space. So the moral is that in collapse models, always there is a diffusion process, a kind of a Brownian motion. And actually, there are specifically theoretical reasons why this has to be the case. If you want to collapse, you have to have this classical uncertainty about the motion of the system. Otherwise, you would do faster than light signaling, and not only because it is here with us, but again, I acknowledge this, the understanding of this to Nicholas in the late 80s. So collapse can with noise. Okay, so what are the pros and cons? So interferometric experiments, these are the direct tests. So they are a direct test of the superposition principle, a direct test of collapse models. You create a superposition, use interference, then there is a superposition. There is no interference, then something goes wrong. On the minus side, it is extremely difficult to achieve this experimentally. Non-interferometric experiments have the opposite properties in a way. So on the minus side, they are a direct test of collapse models, but they are an indirect test of the superposition principle, because you can test the noise even without creating a superposition. You can test whether the noise is there or not. And so it's like with gravitational waves. Gravitational waves indirectly were discovered in the 70s when you had this beautiful accordance between experiments and observation with the loss of energy in spiraling neutron stars. So there was, in a sense, gravitational waves were already with us since decades. But of course, LIGO made a big change because you had a direct observation of gravitational waves. But also those that indirectly discovered the gravitational waves won the Nobel Prize. So it was equally important in a way. On the plus side, it's much, much easier to perform non-interferometric experiments precisely because you do not have to create a large superposition. So while we wait experimentalists to improve technology and to create a superposition, we can work with non-interferometric experiments. Okay, so how do you use these non-interferometric experiments? Well, in any way you want, but we consider three typical situations. We consider cold atoms. So if you have a cloud of cold atoms, then without the collapse, the cloud will not expand too much. But if there is this extra diffusion, the cloud will expand much faster. And you can see that experimentally. Experimentalists have a very good control on clouds of cold atoms. So this is one option. Or you can monitor the behavior of charged particles. Charge plus acceleration, it's a noise, so it's acceleration, means the emission of radiation. So collapse models imply that matter, so that photons should come out of matter because there is this noise everywhere. Of course, it's a very low rate of photons, mainly in the deep infrared. You will never see anything happening right now. But if you go in a very clean environment like an underground laboratory, and if you look for very rare events, this is what high energy people are experts in, then you might hope to see something. And this is what I will talk about. Or you can take optomechanics. You can take a cantilever. A cantilever, so it's basically a pendulum. It is either really a mechanical pendulum, or it's a levitated with some field, but it's basically a pendulum which oscillates according to quantum mechanics. If you cool it down, it will not oscillate much, but according to collapse models, there is this noise that keeps making it oscillate in a random way. And then with some spectroscopy, basically you have a very powerful magnifying glass, which will tell you, through which you can monitor very accurately the motion of the pendulum and see how much it jiggles around the equilibrium position. So these are very sophisticated, very refined experiments, state of the art, which we use to test collapse models. Okay, so the test of the Diauchy-Penrose model. Okay, I still have some time. Yes. So the test of the Diauchy-Penrose model. So first one thing. So as I said before, so the model was meant to be without free parameters, but actually you need a parameter because the Coulomb potential gives you divergences every time you want to integrate it. So it's a usual problem with the point particles in gravity or in electrodynamics. You have a divergence because of the Coulomb potential. 1 over r doesn't go to 0 fast enough. Regularizing the model means basically to replace the point-like particle with an effective extended particle with some radius r0. The smaller r0, the better the point-like approximation. So actually you need a parameter r0 in this model. Diauchy suggests for this effective size of particles the Compton wavelength, because basically it's one way to measure the threshold between a non-relativistic and a relativistic regime. And this is a non-relativistic model, so it has a limited range of validity, and the Compton wavelength is a natural way of measuring this, of assessing this limited range of validity. Penrose instead said something different, said take a crystal, take somehow the wave function of the nucleus, and compute and use so the story is much longer, but I want to make it longer. Take the effective size of the wave function in the nucleus, so 10 to the minus 10, 10 to the minus 11, more or less, and use that as the effective size. So it's so for Penrose, the size R0 depends on the kind of system you are considering. In a crystal, it has a value. In another situation, it would have another value. Okay. Then, so you basically, so testing the DP model means basically setting a bound or on R0. And that's what we did, actually. We did an experiment that appeared on Nature Physics earlier this year. So we computed the photon emission rate from a crystal. So in the crystal, you have the nuclei and the electrons. The nucleons, so the protons in the nucleus in the nuclei, and the electrons are charged, they would emit radiation. Then you compute the emission of radiation, and under a suitable approximation and in a specific range of frequencies, which are in the X-ray region, the rate takes a simple expression, which is the one that I present in the slide. I do not want to comment too much. You can see there are all the constants of nature, basically, except for, well, I mean, even h bar, depends what you want to measure. This is the number of photons emitted per unit frequency. You have capital G, gravity, the electric charge, the electric constant, the speed of light, the number of nucleons, n. So the bigger the crystal, the more photons should come out, quite intuitively. And then you have a dependence, 1 over the cube power of R0, which is important from the experimental point of view because it makes the experiment difficult. If you want to improve the bound order of magnitude, you have to increase the sensitivity of the experiment by 3 orders of magnitude. And experimentalists hated that. It would be, so it's very difficult to test, to put a bound on this model. It depends on the inverse energy of the photon. You see 1 over omega k, which means that it would be easier to do the experiment in the infrared region, but it's much more challenging, or at least for our collaborators, it was much easier for them to do it in the X-ray region, where you have a almost a full control over the emitted X-rays. Okay, so this is the theory. This is the experiment. I'm not an experimentalist, so basically I'm just showing you the pictures. From the right to the left, you have the Gran Sasso laboratories from above, from inside, and then you have just a picture of the detector. It's a germanium detector, so it's just a box of germanium, and inside it there is all the electronics in order which counts the number of X-rays which are emitted by the germanium itself. Everything is shielded and underground in order to remove every possible, more or less, of course, source of noise. These are the data. So on the bottom right, you see the spectrum, which was measured over a period of 2 months, 62 days, so 2 months. And so you see that when you move to the left, it means at lower frequencies, this is not the infrared, but let's say towards the infrared, but you're not in the infrared here. You see that there is a lot of noise. You do not have a good control of the spectrum. If you move to the right, so in the full X-ray region, then you have a better control of the noise. And we consider basically the green area, which is represented in the picture and which is emphasized on the left. And you see that on the left, and you see that over 2 months, the experimentalists measured 576 counts. So single counts. You can easily do the math and see how rare these events are. But even more impressively, out of these 576, they were capable of giving a physical explanation to 506 of them. So it's like what I was saying before. You do an experiment, you have decoherence, you theoretically model decoherence, and so you subtract decoherence, and then you analyze what is left over. Here it is the same thing. So from many of these X-rays, they had a physical, they could give a physical explanation of why they came out, some radioactive activity, whatever it is, and they could justify 506 of them. So you're left with 70 of them over 62 days, so basically 1 per day. And we use that data to bound the parameter R0 of the GP model, and this is the result, basically. So you just have on the axis the possible orders of magnitude of values of R0. From basically the nuclear scale, 10 to the minus 15, to the atomic scale, 10 to the minus 10, and onwards. The red ball, the red balloon there, or the red circle there, is the theoretical value of R0, which you would compute following Penrose's prescription. And then the bars are exclusion regions. So the red and the green one and the blue one were already present in the literature before our work, and the green one instead is the outcome of our analysis. And so you can see that every value of R0 up to 10 to the minus, almost 10 to the minus 10, and so in particular the value computed according to Penrose's criteria is excluded experimentally. The moral, just to give an intuition, is like with GRW. If you make the Gaussian thinner, you destroy matter. You accelerate electrons too much. You make a radiation come out, too much radiation. With R0, it is exactly the same story. The smaller value, the inverse of R0, actually, not R0. The inverse is the same. Is actually the same story. So no, R0. I'm confusing now. So small values of R0 are excluded because the collapse becomes too strong and it would give rise to physical effects which are excluded experimentally. So the equations are the same, so the moral is the same. So what is the conclusion? And then perhaps, I don't know, I'm close to the end. The conclusion about that. So the Dioschi-Penrose model, or according to the original idea of Penrose, is excluded experimentally. This is the simplest way of implementing the collapse related to gravity. Is this the end of the story? No. I mean, no, because you can try to refine the model. You can refine it. There are unreasonable ways of refining that, or there are reasonable ways of refining that. And actually, Penrose has arguments according to which he thinks that he can escape this result. And I leave him to discuss that. Okay, so I will skip the tests about the CSL model because I'm running out of time. So since it is also a workshop about philosophy, I'm embarrassed, but because it is not my field of research, but I will tell you something about an ontology associated to collapse models. I'm sure that most of you there in the audience can say these things better than me, but I just say something. So you have this about the ontology of collapse models. So you have this wave function. The wave function lives not in the real space, like physicists usually think of, but even if they know, it lives in configuration space, or it lives in configuration space. So you have to do something. And there are, as far as I know, three possible ways of attaching ontology to collapse models. So the wave function ontology. So David Albert, if I'm correct, also Philip Pearl. So the idea is that there is only the wave function, like in many worlds, if you wish. But now this wave function is not delocalized in space. For macroscopic objects, it is localized in space. So one positive side of it is that it's an economical way of looking at things. At least David Albert, that once I talked to him, would say this is a strong point. From the minus side is how to recover the world as we see it from this actually from this wave function, which does not live in real space. So you need to recover real space, or at least our perception of real space and this kind of thing. So it's so from the theoretical point of view, it becomes a quite challenging program, but possible. So there is the flash ontology, which was first proposed by Bell and later supported by Tumulka. So here we go to the GRW model. So you know that these collapses occur randomly in time and randomly in space. And then the idea is that these flashes are the reality. So the GRW is a theory about flashes, and all the dynamics, all the business about the dynamics is just the way to give a dynamical, a stochastic dynamical law for these flashes to occur in space and time. I am a cloud of flashes. You see me somehow moving continuously because these flashes occur so frequently and are so dense that they give a sense of continuity over space and over time. So on the plus side, it has a clear ontology. On the minus side, it is, at least for me, a questionable ontology, because if you take an atom, a flash never occurs. So in its technical sense, an atom doesn't exist. So the picture in the double slit experiment, where you have a molecule or an atom that goes through the double slit, actually nothing goes through the double slit. It's just a game of dynamic evolution of wave function in order to give in order to cause a specific pattern of a specific picture, the interference pattern on the screen. But technically, nothing goes through the double slit because for single molecules there is almost never a collapse in space. I personally would dislike it, and also because of I'd rather take a continuous dynamical evolution in place of a discrete one, but this is more an aesthetical reason probably. Or there is the mass density ontology. The mass density ontology basically is just a way to project in the wave function down to real space. You multiply by m and you have a mass density. So I am really a mass density continuous over in space and moves in time, and the mass density of myself, it's is basically localized here. There is nothing in here, and that's why you see me here. And the dynamical and the collapse equation guarantees that my mass density distribution will never be half here and half there. The mass density of an atom is half, literally, the atom is half here and half there in the double slit experiment. But as soon as you want to check whether it is here or there, then you interact with the atom, you cause the collapse of everything, and the atom and the mass density will collapse into one place, all the atom here or the entire atom there. So again, on the plus side, it has a clear physical picture. On the minus side, again, it looks a kind of ad hoc, because it's not like in Bohm mechanics where you have the particles which are guided by the wave function. Here you have really the wave function. You just are in a kind of artificial way projecting that down to real space. My personal take about that is that I wouldn't take any of them, because I think the collapse models are phenomenological models. So I'm not so much passionate of doing the ontology of phenomenological models. I think that the theory of nature is something radically different, where the wave function emerges phenomenologically, so there is no wave function. And so I wait for the new theory to come. I don't have it, unfortunately. Okay, I think I'm running out of time, right?
Yeah. I was going to say maybe try to reach the conclusion so that we can have a discussion session.
The conclusion is thank you for the attention. And I acknowledge, so my research group, the people I enjoy collaborating with, the funding agencies, and thank you for the attention.
Thank you very much. We can have a round of applause. And so we will have around 15 minutes of questions. So put your name in the conversation, and I will take the name. So we have first. So let's start right now. We have Howard, who had the question during the talk. Howard.
Thank you. So thank you for the talk. And I've really went through spontaneous collapse theories in enough detail. So thanks very much for that. I'm interested in decoherence rates versus collapse rates. And you already mentioned a little bit about that in your answer to the previous question. But my question would be, does the collapse frequency lambda affect the decoherence rate directly? And if not, do you know of any like realistic systems, how these two rates compare? So is one of them much faster than the other one, for example?
What do you mean with does the collapse rate affect the decoherence rates? That I'm not sure I understand what you mean with that.
Yeah, so I expect it doesn't, but I would have to.
It doesn't. So let's say that. So with decoherence, I mean with an interaction with a physical and non-physical environment. So standard quantum mechanics, there is an environment I cannot control. I have decoherence. So for me, so that's decoherence, and then there is the collapse. So the two things are independent, and they just add on top of each other. So if decoherence is stronger, you don't see the collapse. If collapse is stronger, you don't see the decoherence, to say. Now, which of the two wins? So the answer of course I'm simplifying things, but the answer is which of the two wins. So well, I can tell you. So basically, so let's take this picture here. Which is basically the exclusion plot for the CSL model. Basically, in all the colored regions, basically, the collapse would be strong. It would be stronger than decoherence. So the collapse would win over decoherence. And then you should see the collapse effect. No collapse effect was seen. And so these values are excluded. So I'm saying this because there is, so which of the two wins depends on the value of lambda. So if you take lambda strong enough, then collapse will win over decoherence. You should see it in experiment. You don't see it, and so these values are wrong. In the white region, instead, you have values of lambda which are weak, which make the collapse weaker than decoherence or weaker than the resolution of your experiment. And then you have to ask the experimentalist to do a better experiment. I don't know if that answers the question. Otherwise, ask me again and we'll try to answer.
Maybe we should keep on the other question, because there is a lot and we don't have much time. So next is Wayne Neville.
Okay, thank you. This was a really great talk. I have a comment and a question. The comment is on your slide towards the end where you're talking about a collapse ontology.
Okay,
I think that there's a view that's left out that is actually Phil Pearl's view. And that's the idea that you've got a quantum state, and what the quantum state is telling you about the world is that physical quantities don't have precise values. You have a sort of distribution associated with any quantity, and that's what there is. But we'll ascribe a probability to, we'll ascribe a property to something. So we'll say there's, a real mass density there, for example, when that distribution is fairly sharply peaked. I mean, I wrote a paper about this a couple of years ago, and I sent it to Pearl, and he said, yeah, I think that's pretty, because I was advocating for that view, and I thought it was more or less his. And he said, yeah, I think that's what that is. Yeah.
So basically, can I simplify by saying that there is a mass density only when it's localized well enough? Would it be?
Yeah. So when they distribute, yeah. So it's similar to what Ghirardi and his collaborators were talking about in the mid '90s, when they would talk about a objective or accessible mass density. It's only when, yeah, right. Okay. It's basically that idea applied to every physical property.
Okay. Thank you.
But my question is, a little while ago, one of my colleagues asked me whether the phenomenon of superradiance could be used as a test of collapse theories, where you've got a whole bunch of collective behavior, and you've got a whole bunch of atoms in superposition of radiating or not, and then they all go together.
Okay.
Is there any is there any prospect of using that sort of thing to get bounds? Because it's the sort of collective behavior of a large number of atoms.
Yes. No. So so the general answer, of course, is yes. In principle, yes. But I don't have a good enough intuition about the phenomenon to really tell you whether you have hopes to challenge collapse models or not. That I cannot do. I understand the motivations of your questions, but I'm just about the details to really tell you what I expect from the calculations. I should do that.
Okay, thanks.
Sure.
Okay, next we have Alberto. Alberto.
Hi, thanks. First of all, thank you very much for the presentation, and very interesting. Also, congratulations to having found a way to use the germanium detector of Gran Sasso, which
thank you.
Is underused. I've seen it being built. The question is about your 576 events. You mentioned, you said 506 were excluded. 70, they contribute to calculate the bound. Can you say something more about how the 506 were excluded, and if there is an intuition about the 70 other than speculative? It could be something else.
So now that's for me it's a difficult question, because really it's a technical. You asked me a technical question. So basically there is. So I learned that while working with the experimentalists. So there is the real treasure of these collaborations is not so much so there are two treasures in these experiments. One is the device, so a clean germanium, in order to pure germanium, so ultra pure germanium, in order to have a full control, but that you buy at some point. But the real treasure is the Monte Carlo simulations, which is basically which simulates the behavior of the detector. So what happens? It could happen that this detector has some radioactive nuclei. It's ultra pure germanium, but not 100% pure. There is not just only germanium. There are also other atoms of other species, and one of them can decay. And when the nucleus decays, it emits an alpha particle, for example. The alpha particle travels, and then it hits another atom, and by hitting the atom, it makes it emit a photon. The photon is absorbed. So there is a huge simulation of this event, which has been elaborated from it over decades, that take into account as many of these details as possible. Another option is a shower of cosmic rays is capable of crossing, some of them is capable of crossing the mountain in Gran Sasso and hit the detector and again cause a photon to come out. So basically, so the 500, sorry, are basically the result of these impressive simulations where the experimentalists thought of every possible physical cause of photon emission, which they're not looking after, something that happens in the detector but not comes from new physics, so to say.
Thank you.
So this is the first part. The second, so what about the 70 which are left over? Well, no one knows, in the sense that you can what they say, you can characterize the detector even better. So you can add other physical processes that you know of, but were not taken into account, or perhaps you didn't think of. Or perhaps there is new physics that they don't know. So these detectors were made, for example, for dark matter. So they want to find the dark matter. So a characteristic signal coming from this of dark matter, and then you have to exclude all other physical explanations for the X-rays, so that what is left over can be attributed to dark matter or to collapse or to something else.
Yeah, because even if the ratio is very small, 70 events is large.
Yes, it's not. It's not.
Of experience on the detector.
No. There are actually, we are talking with other. So let's say this is the first dedicated measure. Now we are talking with other experimentalists, with Gerda, but also with the people in Gran Sasso as well. And with a better characterization, you can easily improve the result by 1 or 2 orders of magnitude. So you can do much better, but there is a point that that doesn't help much because of the theoretical formula. If you improve by 2 orders of magnitude, since the theoretical formula goes with the inverse cube power of R0, a 2 order of magnitude improvement in the data analysis gives you less than 1 order of magnitude improvement of R0, which could be good from high energy people. I mean, they don't work in terms of orders of magnitude, they work in terms of factors, 1.2, 2, 3, 4. But here, as a theoreticians, we are talking in terms of orders of magnitude. So an improvement of less than 1 order of magnitude is not dramatic for us, theoreticians, even if it's an extreme challenge for experimentalists.
Okay, next question is from David.
Hi, Angelo.
Hello, Davide, ciao.
Ciao. 2 quick questions. The first, after the experiment that you have performed, is like the parameter R0 becoming too big if you don't have other dynamical parameters? Because now it seems to me that the particle in Penrose model is like the size.
Yes, I agree with you. I usually in my talks I don't want to be negative. My personal take is that the value of this parameter is unphysical now, and so I wouldn't. So I don't think that the model can survive the way it is. There must. So you have to add something.
Unless one adds other dynamical parameters.
Yes, okay. You have to add some other. You have to do something. But if you take it as it is, I wouldn't say okay. It's a big model with a larger R0. For me, that is not a viable option.
Thank you. And the other question was about the relation between decoherence and GW. There is a way to detect experimental deviation using recoherence. That in decoherence we can recohere in some regime hypothetically, and in GW the same master equation will give you in any case an irreversible collapse.
Well, yes, there could be a way. Yes, no, you're correct, but I would say that it's a way to distinguish between GRW and certain types of decoherence, but not any type of decoherence, because, for example, collisional decoherence is irreversible. It wouldn't allow you to recohere.
So the challenge is to understand if those models of decoherence that can be compared with GRW are irreversible or not, if you can recohere those models or not.
No, yes. So you can make it. Yes, you can distinguish that. Yes, but the challenge would be with the other ones.
Okay. Okay. Thank you. Thank you, Angelo. Grazie.
Okay. Thank you. So next is Guido.
Thank you. Well, the question is very simple. What is the latest about testing CSL, and what's expected?
So it's the picture here. So this is the state of the art at the moment. This is, as far as I know, it is, but it should be. So this is the state of the art. So again, so the gray region is a theoretically excluded region in the sense that if you pick values here, then there would be macroscopic objects which should be in a superposition. So this is not so the gray region is not an experimentally excluded. It's just based on the idea that if collapse models are work, then they should justify the classicality of every macroscopic, even small but macroscopic object. The colored area instead is refers to experimental evidence. You see that the value of Adler is basically ruled out, at least for standard CSL. Then you might try to recover it with modified version of CSL, but it's modified and it's only this white region, which might look small, but I mean, if you count the orders of magnitude, there are still quite a lot. So this is the latest. So we won a grant, for example, a European grant to improve the situation, and it will correspond morally. We will see what happens in the end, morally to the red box here. So it will be a vast effort, 4 years of work and millions of euros, a dedicated experiment to reach that, which is experimentally a great result, but still a long way. Okay. Before you see something or you exclude everything.
Okay, thanks. Good luck with that.
Thank you. I mean, the pandemic is ruining everything because labs are closed, but we will see.
Okay, next is Marcus.
Hi, Angelo. Thanks a lot for this really, really nice talk. So labs in Vienna are open, by the way, for a few people at least.
Yeah, no, they are open, but I mean, the damage was quite large.
Yeah, that's right. So Angelo, I have two quick questions. The first one refers exactly to the slide. There was a recent experiment published 2 weeks ago from the LIGO community. They feedback cooled one of their LIGO mirrors. So this refers to your optomechanics experiments down to a few phonons only, so an effective temperature of 17 nanokelvin or so. And I'm wondering how this relates, would relate in this overview here, and if you have looked into that already.
So can I answer quickly to this? Then
yes.
So I haven't. I will. So LIGO is the blue here, the blue line. Can you see my?
Yes.
Okay. So basically, this will basically just shift it rigidly down.
Okay.
So how much? I don't know. I have to do the calculations.
Okay, I would be really curious to see that.
Yes, I will. Thank you for telling me.
The second question, I'm wondering, what is your personal threshold above which in those experiments you would say there is no need for collapse models?
Can you, sorry, so that you mean because they are excluded experimentally?
Yeah, well, you never can exclude them, right? But you will at the end of the day, let's say these experiments will push the parameters further and further, and I'm wondering where's the threshold above which you would say now.
Yeah, it's the white region basically. It is the white region more or less. If you really cover the white region, is the end of the story.
Okay. Okay.
Of course, I mean I don't expect really, I mean, fully cover that, because even if you leave a small piece out, I mean, that would be really surprising that it is exactly that one. Let's say that morally, if not technically, if you cover the white region, that's the end of collapse models. But let's hope for that you will see something, because you will see you will win the Nobel Prize, you know, Marcus.
It would be certainly less boring.
Definitely less.
Okay, so for those who want to take a 5-minute break before the roundtable, you can, but we have a last question from Anthony. So Anthony Valentini, so Anthony, you can ask your question.
So, well, my question was almost just answered, but I just on this point of, are there realistic prospects in how many years could we be in a situation where basically they are completely ruled out? Is that a realistic prospect?
No, that's a question for Marcus. He is in a better position than me to answer, but I think it will take time to go down there. Marcus, can you answer to that?
Well, I mean, I gave a rather pessimistic view on the interferometric experiments yesterday. Yeah, but so this is why I'm wondering. So this latest experiment by LIGO, now we really involve large masses. We have like 20 kilograms, and there was an experiment a few years ago where they cooled a mode of the ton scale Weber bar, the Arrigo, I think, in Italy, down to a few phonons. So I guess such experiments, well, will push this bound quite down, I hope.
So I don't have, I'm not in a position to answer your question really, because it's a technological experimental, and I wouldn't be able to answer. So.
Okay, well, thank you.
Sure.
I hope in our lifetime.
I hope so too. Yes.
Okay, so let's all thank Angelo for the talk and the discussion.
Thank you very much.
Thank you very much. And yeah, we have, I guess, 5 minutes break before the roundtable. So
It was great seeing you, Angelo.
My pleasure, man.